Welcome back after the short break. Now I'm wearing my other hat as a moderator of the spotlight session. I'm very happy to have 4 of our PhD students in the cluster here today this afternoon and have them talk about the progress in their respective projects. The first one is Jonas Ditz. He is working on a project that is jointly done by Nico Pfeiffer, professor of medical informatics, and Matthias Schwab in the medical school. Here you go, Jonas.
Thank you very much for this introduction, and thank you for the opportunity to introduce my project or our project to you. We started this project in March this year, and I would like to introduce the motivation on the next slide to you, a brief motivation for this project. So in our project, we are set in the field of precision medicine, which is a medical approach that tries to stratify patients based on individual factors rather than using a one drug fits all approach. The benefit of such an approach can be seen in multiple examples. To stick to the scope of our project, I will keep focus on the example of drug response. So drug response is a crucial information that we need to know in order to determine if we can treat a patient using a specific drug, and if we can answer this question with yes, also to determine how we need to treat the patient with this drug. The drug response of a patient, however, is highly affected by the so-called ADME phenotype of this patient. ADME stands for absorption, distribution, metabolism, and excretion, that you can see on the lower left part of this slide, and describes the 4 main stages that a drug is going through within a patient's body. So in order to be able to say something about the drug response, we need to predict this ADME phenotype of our patient. And the ADME phenotype is highly affected by the so-called ADME genes and the genetic variation of these genes. ADME genes is a group of about 300 genes that affect different processes in these 4 main stages. However, just the genetic variation is not enough to reliably predict the ADME phenotype. There are several other factors that also influence the phenotype, like epigenomic factors, transcriptomic factors, but also proteomic, metabolomic, and microbiomic factors, and even phenomic information is needed to reliably predict the ADME phenotype. Therefore, we need to incorporate all these different data into our models to can reliably say something about the phenotype, and as a direct result of that, about the drug response of our patient. To achieve this reliable prediction, we split our project into 3 phases that you can see on the next slide. And in the first phase of our project, we want to extend deep kernel approaches to incorporate kernels that in the past have already proven to be beneficial for different data that all affect the phenotype, the ADME phenotype of our patient. Moreover, we also want to incorporate the multi-kernel learning framework into our model so that we can utilize all the different data and use all these different information in our model to predict the phenotype and the drug response. However, we are in a medical context here, and to be able to utilize our model then in a clinic or in a hospital, just predicting a phenotype is not enough. We also need to be able to explain how a certain prediction was calculated. To achieve that in the second phase, we want to make our model explainable by, on the one hand, using the interpretation capabilities provided by the kernels that are incorporated into our model, and combining these with methods from the field of explainable AI, for example, like layer-wise relevance propagation, to create a model that can not only predict ADME phenotypes and drug response, but also give insight and explanation about how this prediction was computed. And then when we have these explainable models in a third phase, we want, of course, improve the prediction of ADME phenotypes, but also with our colleagues at the Margareta Fischer-Bosch laboratory in Stuttgart, who are medical experts, we want to gain further understanding into the underlying mechanisms that are responsible and that are affecting ADME phenotypes, and as a direct consequence, the drug response of our patients. All that's left for me to do is thank you all for your attention, and now I'm really happy to answer any questions from the audience. Thank you very much. I cannot hear you.
Okay, so sorry about that. A couple questions, quick answers. Is the problem inherently sparse in terms of which people get how much of which medication for which disease?
How much of which medication for which disease? So, not sure if I quite make the connection here. So the amount of medication that we need to give a patient is dependent on how this drug can be absorbed from in the patient's body, can be metabolized. So I'm not sure if it can be said to be sparse,
okay,
because the amount of drug is dependent on the phenotype that we want to predict. So it's a result of our model.
And is this kind of high precision medicine already used in the clinics? Do you know examples where that is the case?
Unfortunately, I cannot give a real example. I have not a concrete example, specific example ready, but so it's currently still more on the research side. So it's a quite recent shift in the medical research to focus more on individual factors of a patient, to really be able to get to design treatments that are really precise for individual patients. Yeah.
Okay. And which directions do you want to extend your deep kernel approaches to?
So currently we are planning. So we do not have any results yet because we are just in the start of the project, in the starting phase. But we want to. There are numerous kernels that provide beneficial information and interpretation capabilities for the data science. For example, the oligo kernel, and we want to extend the kernel networks to be able to use these kernel functions.
And do you see advantages of the kernel framework over deep learning?
I see the advantage in the interpretability, because the kernels provide already a lot of information that can be used then in interpreting and explaining the result, which is really important if we want to gain further understanding and not just predict a phenotype, but also because if we want to use this information, then we need to say why we predicted a certain phenotype of the ADME phenotypes for a patient. And in my opinion, here the kernel method or the interpretability of kernels are highly beneficial.
Cool. Yeah, thank you for this introduction into precision medicine. Next one up, and that's all. Thank Jonas for his presentation. Next one up is Susanne Zabel. She's a PhD student with Kai Nieselt in the Center for Bioinformatics and Philipp Hennig. There she is.
Hi.
Hi, Susanne. And she will talk about visualizing uncertainty in principal component analysis.
Thank you. I want to directly start with my first slide. Dimensionality reduction techniques can be used to visualize high-dimensional data by projecting them down into a lower dimensional subspace. These projections should be meaningful, such that properties of the data in high-dimensional space is still present in the low-dimensional representation. One of the most famous dimensionality reduction techniques is probably principal component analysis. It finds orthogonal directions in the data that contain the largest variance, and by that being meaningful. These directions, which are also called principal components, can be found by computing an eigendecomposition of the covariance matrix of the input. And these eigenvectors then correspond to the principal components. Next slide. The conventional PCA simply uses a set of input points as an input. However, data might come with uncertainties or variances, which can highly influence the outcome of the projection. We, in our version of the PCA, want to include these uncertainties as they have this high influence. So starting from a distribution over the input, we approximate a distribution over the eigenvectors and then visualize the outcome in an animated fashion, which I will show you later. But first, on the next slide, I want to introduce what might be sources of the uncertainty of the input. So imagine a medical setting where we measured several variables for several patients. Each of these variables is a measurement and might come with some measurement error. On the other hand, samples might have different uncertainties. For example, if they were measured or the data for this patient was recorded by different persons, which have different experience level. So both the variables and the samples uncertainty are included in our model. On the next slide, I want to introduce a little bit to the mathematical background. So we assume that there exists a ground truth matrix Gaussian distribution over our input. Unfortunately, we don't have access to this distribution. We only have access to a measured version of it, which includes the variables and the samples noise, which I just explained before. Using some Bayesian inference and Taylor approximation, we can approximate a distribution over the eigenvectors. As this is the key distribution of our method, I want to quickly have a look on it on the next slide. So as you can see, this distribution over eigenvectors and eigenvalues is a normal distribution with some mean and some covariance. The covariance contains a Jacobian, which is basically a derivative of the outcome of the PCA, which is in our case the eigenvectors with respect to the input, which is the data. So it's a derivative of a function which includes an eigendecomposition. And it's just recently possible to efficiently compute such derivatives by using automatic differentiation, which is implemented in some Python packages, like, for example, JAX. So how do we now come from this distribution to a visualization? This I want to show you on the next slide. So we will draw samples from this distribution in a clever way. And by that, I mean that we try to traverse through this distribution to get an intuition about its behavior. We then take the samples and transform and project the data accordingly. And each of this projection builds then a frame in an animation, which I will show you in the next slide. So as you can see, this animation gives you or provides an intuition about the stability of your projection. I want to end my talk on the last slide with some limitations in an outlook. So the problem right now is that the Jacobian gets quite huge for an increasing number of samples and especially dimensions. And in order to make it an efficient tool and also apply it to large-scale data, for example, transcriptomics data, that's a point I have to work on. Furthermore, I want to compare this method to other stability methods, which are usually based on sampling. And I also want to finish the paper that I'm currently writing about my first findings. As next steps, I can imagine to assess more the importance of individual data points, as this visualization gives more an overall view, and also maybe assess some outliers. And I want to combine all this with meaningful visualizations. Thank you, and I'm happy now to take your questions.
Yeah, thanks, Susanne, for this interesting introduction to your project. We already have a couple of questions and we'll go right into them. So could you comment on the links between your method and approaches like probabilistic PCA? Giovanni is asking.
I don't think I can do it right now. No, okay. Sorry.
So for the, maybe you guys can discuss that after the talk.
I have to go into the details of probabilistic PCA again.
So for the samples that you just showed, what is the exact dependence in the sequence of samples, and what would be a compact way to summarize that?
So you meant the samples that I
animation.
Okay. What's the dependence? Okay. So instead of picking only one sample from this distribution, I will draw one random sample, and there will be a whole sphere of other points of the same probability. And we then decided to just walk in one direction on this high-dimensional sphere in a big circle, and depending on the number of frames, collect the samples from this circle. And by that, we walk through, let's say, the whole space of samples.
But then it's
a bit hard to.
But it's not a posterior, or something like a. So it's just one cut through that distribution.
Exactly.
Okay. And does your framework allow to deal with missing data, or include missing data in addition to this kind of variability?
Not yet.
Okay.
So we haven't thought about this.
Okay. Okay, cool. Then thanks a lot, Susanne. We can all thank her. And the next one up is Paolo Mazza. Ah, there you are. From the groups of Igor Lisanovsky and Sabine Andergassen in the physics department, he will talk about learning quantum dynamics.
Okay, so good afternoon, and thank you for the introduction. So in this very short talk, I will introduce you to our project that concerns the investigation of the quantum dynamics by means of machine learning-oriented algorithms. So in the next slide, I will just state general framework. So let's imagine that we have a quantum system that is composed by an enormous number of particles that interact among themselves. So in principle, we could study the dynamics of every single particle by solving the single particle equation, the Schrödinger equation, and follow it in time, and I don't know, counting observables and so on. However, when we have interaction, there are some collective phenomena arising that make this time evolution highly non-trivial. And in particular, there is a statistical behavior arising in the system, and that can be summarized as some irreversibility that arises from a reversible process. And this is due to the fact that there is an information scrambling in the system due to an entanglement grow among different parts of the system. So, okay, so you can see in the next slide, you can understand that this is a very challenging problem. I mean, studying the dynamics of these systems that are composed by an enormous number of interacting particles is a very challenging problem for physicists that physicists are trying to puzzle for decades, both with analytical and numerical methods. So now in the next slide, I would like to focus on our study case. We are considering, we study spin systems, one-dimensional spin system. A spin system is a quantum system in which the local variable are binary, basically. So 0 or 1 or -1 or 1. This is arbitrary, and we can see that this kind of system can, in physics, they find application in several different fields, from information theory to quantum statistical physics, but they have application also beyond the realm of pure theoretical physics. For example, the classical counterpart, they can be employed also in neuroscience. So now, if we have the state of this system is described at every instant time by this mathematical object. It's a density matrix. This mathematical object it's kind of complicated object because scales exponentially with the system size. But we can basically divide two parts. One is on the diagonal that describes the stochastic dynamics of the time evolution. And the other part is the off-diagonal part of this matrix that describes the pure quantum correlations. And as we can see in the next slide, we know that theoretically there are some quantum systems for which the dynamics is fully described by the stochastic part from the diagonals. And these systems are usually called constrained quantum system. An example is, for example, this blockade quantum system, in which we can only explore the Hilbert space in which we don't have two contiguous excitations. So basically, the dynamics is happening in a subgraph of the entire Hilbert space. So let's say that the complexity is no longer exponential. But despite their simplicity, these systems can describe a plethora of different physical phenomena, going from glasses to gauge theories. So as we can see in the next slide, so we want to study this system. In particular, we want to design, we are designing a machine learning algorithm that can learn the time step, that is the evolutor that takes as input the probability vector at time t, and gives as output the probability vector at time t plus beta t, where beta t is a discretization of time that is chosen a priori, but must be carefully chosen, because of course this approximation can lead to some errors. And in particular, we are designing both MLP, so it's multi-layer perceptron, but also a variational autoencoder in order to study the dynamics. And so I hope that there will be results very soon, because this is highly non-trivial, because as we can see in the next slide, understanding, if we understand that it's possible to learn the dynamics of the diagonal elements of this density matrix, is something very important, because it means that we can design a code that learns how the systems thermalizes. So that means how the correlation in the system scrambles, and we can have also information about the local correlation, because they are already in the diagonal elements of the density matrix. We know theoretically that there is a class of quantum system for this. This can be done for sure. So we are just find how to design the architecture of the neural network in order to make this possible. And a successive step will be to try to use convolutional neural network to try to learn these dynamics in a scalable way. What I mean is that we train for a given system size L, and we try to extend to use our code also for forecasting the dynamics for a bigger system size. And this would be a really interesting achievement. And with this, I conclude, and I will thank you for the attention.
Yeah, thanks, Paulo. So one question from myself to start things off. What is the kind of data that you want to use to learn from? Is this observations of some real quantum system, or is that observations from some simulation of a quantum system?
Well, we are using actually right now the data that comes from simulation, because we can for a small system size we can simulate exactly the dynamics with the algorithms that are called exact diagonalization. We can generate this data, but of course this system can also be realized in in a laboratory. So it's also in principle possible to use real data. But I mean, the point is, as I told you, would be really to train this this network with exact data coming from a simulation for a system size, for example, of L equal 10 spin, and try to extend using our algorithm to 20 or 30 sites. And this is at the moment is not possible. It's not possible to simulate exactly this system for L bigger than 20, let's say.
But isn't one problem in the simulation the fact that 2 to the 20 is just a big number, and
exactly.
But how do you think this goes away by using a multi-layer perceptron?
Because basically all these spin systems have I mean, at least the one that we are studying, that by the way are the one that are also most interesting for the community, have local interaction. Mm-hmm. So there are no long-range effects. So in principle, it's possible. I mean, since the interaction is local with the use of this convolutional neural network. I mean, at least we want to try this to see if, since the interaction is local, if this can be this can be learned in a scalable way. Yes, it's because the interaction is local. So there is kind of fractality in the dynamics. Let's say.
So one final question. So why are you learning the probability distribution and not the time propagation of the quantum state directly?
Of the quantum state? Well, the probability, okay, so the quantum state, as I showed, there is on the diagonal part, there is a part that I call probability, and the off diagonal, it's the pure quantum correlation. From the probability of the diagonal, we can already gain some information about the quantum evolution of a particular class of system. Of course, it's possible to train a neural network using the full diagonal matrix, but in this case, there is a problem that the number is. I mean, we have more elements basically, and the off diagonal elements are complex numbers. So we have to deal with the fact that they are complex, but instead the probability are just real numbers. So our first approach would be to learn the stochastic part of the dynamics of this quantum system.
Okay, thank you, Paolo. And the final presentation will be by Jonathan Fuhr. Just let's wait quickly while we swap speakers. Okay, here's Jonathan. So Jonathan is a PhD student who started recently in Dominic Papi's group, collaborating with me on causal inference in social science and medicine.
Thank you for the introduction. As Philip already said, my name is Jonathan Fuhr, and I've just recently started my PhD under the supervision of Dominic Papis and Philip Behrens. And we are grateful for the funding from the Cluster of Excellence. The title of our project is Applied Causal Inference in Social Sciences and Medicine. And on the first slide, I want to give an intuition about what causal inference is in general in these contexts. For that, please look at the causal graph in the middle of the slide. In a graph like this, the nodes are variables and the arrows are causal relationships. Here, a researcher is interested in estimating the causal effect of smoking on lung cancer. This is a classical example in causal inference, because for a long time, researchers have doubted whether one can estimate the causal effect of smoking at all. Some have argued that there might exist an unobserved gene that causes both smoking and lung cancer. If that were true, the gene would be a so-called confounder, and the estimate would indeed be biased. This example illustrates some properties of causal inference. It shows that causal questions cannot be answered only from observational data. We always necessarily need some assumptions about the causal structure of the problem. In our example, we could just assume that there exists no gene like this. If there is no unobserved confounding, we can directly estimate the causal effect from the data. Strong and untestable assumptions like this have to be made very often when estimating causal effects in practice. In many cases, these assumptions might be quite questionable. That's why researchers in causal inference are always interested in weakening assumptions. With weaker assumptions, it might be possible to estimate causal effects that could previously not be estimated. And having that goal in mind, several frameworks have recently been developed that combine methods from machine learning and causal inference. So this is the question we want to answer. How can methods from machine learning help to do causal inference under potentially weaker assumptions? On the next slide, I will give an overview of the proposed frameworks. They can be divided into 3 categories, where the first 2 are about estimating different kinds of causal effects, and the third one is about discovering causal structure. In the first category, the goal is the estimation of average treatment effects. That is, effects that are the same across a population. Here, there are methods that try to weaken assumptions about the functional form of the confounding. Other methods try to select the appropriate confounders in high-dimensional settings. And another kind of method wants to weaken the assumption that there is no unobserved confounding. The second category is concerned with the estimation of heterogeneous treatment effects. That is, effects that differ across subgroups or even across individuals of a population. Here, the goal is to weaken the assumption that a researcher has to know beforehand where to expect heterogeneity. And in a third and final category, the causal discovery methods aim to discover the causal structure from observational data. Usually, the causal structure of a problem is derived from domain knowledge. This means that there are already a lot of assumptions when coming up with a causal graph like the one we saw before. The causal discovery methods in this domain aim to learn the causal graph directly from the data. So this is just a quick overview over the potentially promising methods. Our goal now is to find out whether these methods can help to do causal inference in a better way than is common in practice today. We will do this specifically in 2 areas of application, in social science and in medicine. And for that, we plan to proceed as shown on the next slide. First, we will assemble data sets from social science and medicine where these methods might find a promising application. Then, we will use these data sets to assess whether the application of these methods is feasible and valuable in these contexts, and whether we can indeed do causal inference under weaker assumptions. Finally, we will summarize our findings and derive recommendations of best practice. This is supposed to give guidance to applied researchers as to when and how they can use those methods. With that, thank you for your attention, and I'm looking forward to comments and questions.
Yeah, thank you, Jonathan, for this introduction. So Jonathan started in May, so the project hasn't been running for a very long time. One question by Ulrike. In the applications that you have in mind, is it clear what the most important variables are? If not, how would you identify them?
My answer to that would be that we would have to identify the most important variables from domain knowledge, so from the literature, where we could just see what other authors have traditionally thought about these problems, and that would be the traditional way to come up with a causal graph, like I showed. Another way would be just to have a data set and use that for the causal graph, to come up with a causal graph. But there's always the chance that there are variables that we don't have in the data set that are not observed, and that's always an issue. But there are also causal discovery methods that can give hints where unobserved variables may still be.
Mm-hmm. Is there an idea of how many data points are needed for such causal inference methods to work in practice?
not like a concrete number. Most of the results are asymptotic, so are really for large samples, but there's also a literature for small samples. But most of the methods that I've been reading about are in large samples. So yeah.
So Alvaro from our transfer center would like to know whether for your task 2 here to assess the feasibility and the value of the proposed frameworks, what would be your criteria for success?
So in my mind, we would do this in at least 2 steps. One step would be just to implement these methods on simulated data to understand the methods better and to see in which cases of the simulated data they work and in which cases they don't. And then to transfer that knowledge from these simulation studies to real cases and then discuss the plausibility of the assumptions that we still have to make by theory and literature work.
Mm-hmm. Thanks a lot. And the final quick question is, so how can you separate causal discovery from the estimation of the treatment effect? So don't you, wouldn't the variables to condition for also depend on the causal structure?
Yes, usually we cannot do any causal estimation without having any causal structure, at least in observational data. So one way would be to use causal discovery to come up with a graph and then do some causal estimation. Or the traditional way is to come up with a graph from literature, from theory, from domain knowledge. And this can also be combined. One drawback of the causal discovery methods is that usually the output is not just one graph, but you get a so-called Markov equivalence class where there are many potential graphs, and then you would have also many potential estimates.
Okay, thanks a lot, Jonathan, for this final presentation in our Spotlight session. I think the 3 Spotlight session over the 3 days of the conference gave you a peek into what is currently going on in terms of research projects at the cluster. Keep in mind, many of the PhD students and postdocs just started very recently under also quite challenging conditions. So I hope they will continue their good work. We will now have a quick break for 15 minutes. And then at 3:45, please welcome with me Stephanie Jegelka from the Massachusetts Institute of Technology with a keynote lecture on representation and learning in graph neural networks. Thanks a lot and see you in 15 minutes.